Hello, everyone. Welcome to today's lecture on diffusion generative models, also known as score-based generative models. So as far as business, Lab 9, the reinforcement learning lab is due this coming Saturday, as well as your readings for the week and your final project. There are no deadlines in the near future, but just a heads up to have that on your radar. So last time we talked about variational autoencoders and flow-based generative models. To start out today, see if you can remember, match each of these types of generative models to the tasks that they can tractably perform. So if you'd like, you can pause the video, and each one of these types of models can have multiple answers. Okay, so they can perform density and estimation by taking an input X, mapping it through the autoencoder to a corresponding mean and variance, and calculating the probability of that latent vector under standard normal distribution. They can also do sampling by taking a latent vector and passing it through the decoder. However, they cannot perform exact inference, which is mapping each X to one specific probability. On the other hand, flow-based generative models flow-based generative models can perform density estimation, inference, and sampling. If you remember for flow-based generative models, we have an exact function learned between the latent distribution P of Z and the data distribution P of X, and a direct one-to-one mapping between each X and each Z. And so because of that, we can perform density estimation by mapping X's to Z's, and those are exact. So that's exact inference, as well as sampling by sampling a Z and mapping it to an X. GANs only perform sampling. There's no way to tractably perform density estimation and, by extension, exact inference. And autoregressive models. So this is something we haven't mentioned yet, but I wanted to bring up in this quiz because you can think of autoregressive models like transformers or RNNs as a certain class of generative models. If you consider the probability of a sentence x1 to x10, where each x is a word, you can factorize that joint distribution, the probability of x1, x2, x3, etc., as probability of x1 times the probability of x2 given x1 times the probability of x3 given x2, etc., all the way to x10. And because a trained transformer gives us those, at least an autoregressive transformer gives us those probabilities explicitly, we can use that to perform density estimation and exact inference. And then if we sample from those distributions, then we also can perform sampling from an autoregressive model. So I wanted to mention that, transformers actually can be thought of, at least autoregressive transformers can be thought of another instance of generative models that model that joint probability distribution. Okay, so today we're talking about diffusion models. So what are diffusion models? basically, we, again, are dealing with latent vectors z, and we want to learn a function that denoises a sample z into a sample from our data distribution. So a quote from the stable diffusion paper says, diffusion models are probabilistic models designed to learn a data distribution p of x by gradually denoising a normally distributed variable, which corresponds to learning the reverse process of a fixed Markov chain of length t. I wanted to include this just because I think it sums up diffusion models very clearly. Now, it talks about this reverse process of a fixed Markov chain. Let's take a look at that Markov chain. So this is our setup. We're going to set up a Markov chain going from x0 to xt, where x0 is a sample from our data distribution, and x3 is a sample from the standard normal distribution. And our forward, what we will call our forward process, goes from x0 to x3, and that's given simply by gradually adding noise to a sample x0, according to this formula here. Q of xt given xt minus 1 is given by a sample from a normal distribution centered at weighting term times x1 with a variance factor of the identity matrix. Okay, so yeah, that's our forward diffusion process, and that's pretty easy. There's nothing learned there. We're just gradually adding noise to an image. The secret sauce is this p sub theta. We are going to learn a reverse diffusion process, p sub theta, that learns to remove noise from a sample x3 all the way until we achieve a sample from our data distribution x0. And some more details explaining this. So we saw this alpha sub t in this normal distribution for Q. That alpha sub t is going to be a decreasing sequence of values where each alpha sub t is between 0 and 1. And this sequence approaches 0 as the time step approaches the maximum time step t. And a special property of this forward diffusion process is that we can express xt as a linear combination of x naught and a noise variable. And so, yeah, rather than adding noise t times to transform x0 into xt, we can simply apply this formula at the bottom to obtain any x naught. So take a second and think about what would happen as alpha sub t approaches 0 in this formula. So you feel free to pause your video and yeah, think about that question. What happens to xt as alpha sub t goes to 0? So you should probably notice that the first term approaches 0, and the second term approaches 1. So x sub capital T will be essentially a sample from a standard normal distribution centered at 0. Okay, so how do what is our objective to learn this reverse diffusion process? Well, we are going to use the maximum likelihood objective for our data and use a very similar objective to what we looked at for variational autoencoders. So as a preview, we can use Jensen's inequality to derive the evidence lower bound for the log probability of our data. And we're going to subscript that that by 0 because x sub 0 are the images, are the samples from our data distribution, as opposed to x sub t are z vectors essentially. Okay, so on the left-hand side, we have our derivation of the evidence lower bound for BAEs. That should look familiar from last lecture. For diffusion on the right, we have the evidence lower bound for diffusion models. So first of all, we're going to decompose the probability of x naught as the probability of xt times the probability of xt minus 1 given xt, or times the probability of xt minus 2 given xt minus 1, etc. And then we're going to integrate over all t not equal to 0. So this is just rewriting the probability of x0 in terms of the factorized joint probability distribution, p of x0, comma, p of x1 all the way to xt, decomposed as this chain rule of probabilities, and then summed over all x not equal to 0. Okay, then from that, we're not going to show the derivation, but you can derive an evidence lower bound. In this case, we're taking the negative log likelihood, so it's an upper bound, but you can negate that and this becomes a lower bound on the log likelihood. And it basically amounts to minimizing the KL divergence between our forward diffusion process and the reverse diffusion process. And then some further simplification of this leads us to our objective, which is the expectation over x sampled from our data set, noise E sampled from a standard normal distribution, and t different time steps to give us a denoising objective. So let's look at this last line here. Take a look at this last line and see if you can understand where the target comes from and where the learning happens. Okay, so this last line is our denoising diffusion objective. And basically what we're doing is we are taking x naught and converting it into xt by multiplying it by the square root of alpha sub t and adding this noise term. And then our model tries to provide us with the noise that will denoise xt into xt minus 1. And so that will be compared to epsilon sub t, which is the difference between q sub t and q sub t minus 1. So basically, we're trying to train the transit p sub t minus 1 given t sub t to match q sub t minus 1 given q sub t. So yeah, intuitively though, you can know that we're trying to train p, the reverse diffusion process, to match q, the forward diffusion. Okay, so we have this trained model now. How do we sample from it? So essentially, we're just going to iteratively apply this denoising function, epsilon sub theta, that we learned to our two samples from the z distribution. Some papers have shown that this can be interpreted as a type of sampling called Langevin dynamics. where you interpret the denoising function as a gradient of the probability density function over X. And you just follow that gradient to find a local maximum of the probability density function. And that is your denoising process is following that gradient to a local maximum. There are also some variations on this. There's a sampler called the denoising diffusion implicit model, where they actually show that you can skip steps in this diffusion process, which is kind of interesting. And then there's also ancestral sampling, which we're not going to discuss in this lecture, but just know that it's another sampling option for sampling from these diffusion models. We can also perform density estimation. How do we do that? Well, we take a sample x0 or x0, a sample from our data distribution, and we just pass it through Q to obtain a corresponding z vector and evaluate the probability of that z vector under a standard normal. Okay, so this is basically the setup for diffusion models, but there are quite a few variations on these. So we mentioned denoising diffusion implicit models. These recognize that the denoising diffusion probabilistic model objective does not necessarily depend on a Markovian factorization of Q of x sub t. There's nothing in that formula that says that we need to directly go from x sub 2 to x sub 3 to x sub 4, etc. And they show a way that we can skip steps in the reverse diffusion process. And the amazing thing about this is that you can do it using a model trained on a Markovian forward diffusion process. So basically, you can take an already trained diffusion model and sample from it 10 to 100 times faster without any changes to the model. So that's DDIM. There's also a paper that shows that you can generalize this discrete time Markov process to a continuous time, what they would call a continuous time probability flow ordinary differential equation. And so we'll get into that a little more in the end of this lecture. Then you also have conditional diffusion models, which these are perhaps some of the models that you may have seen recently, where they generate extremely plausible images using text descriptions of those images. And then, yeah, one last variation are latent diffusion models, where instead of diffusion happening in image space, for example, it happens in a latent space, which has some benefits in computational efficiency. So conditional diffusion models. There are a couple of ways that we can do this. And I'm going to provide you a link if you're interested in learning more, but there are two basic approaches to conditioning these diffusion models. One approach is to use an unsupervised diffusion model, P of X, to generate conditional samples by using a classifier, P of Y given X. It turns out you can condition these models without them being trained in the first place to be conditional. So that is called classifier guided conditioning. Another approach is what we will call classifier free conditioning. So this is where you train a diffusion model directly to generate conditional samples, P of X, Y, from some representation of Y. So this is kind of the more direct approach. And generally, most most state-of-the-art conditional diffusion models use classifier-free conditioning. It seems to work better when you train your network directly to generate conditional samples. Okay, so we're going to bring this all together to all of these ideas into trying to understand the diffusion architecture. So this is a very computationally efficient architecture that came out recently and which you will be taking a look at in your lab due next Saturday. So here are some elements of stable diffusion. We have a discrete time Markov chain. We are using classifier-free diffusion guidance, and we're doing that via a cross-attention mechanism, which we will explain. We're going to use a latent diffusion model for computational efficiency, DDIM sampling for efficient sampling, and then a UNet denoising architecture. So this is it. This is quite a bit, but hopefully we can break it down. So for starters, we're going to start with a sample X in pixel space. We will pass that through an encoder E to obtain a Z vector in latent space. We then can apply a forward diffusion process, which gives us Z sub capital T given Z0. And that this forward diffusion process is just given by Q. Then we're ignoring conditioning for now. For our reverse diffusion process, we are going to have a UNet architecture, which is given inside this smaller green box, conditioned on that Z vector Z sub T, which is a sample from a standard normal distribution. And we pass ZT through that denoising UNet, capital T times, to arrive at a vector Z0 in latent space, which we then pass through a decoder D to obtain a sample X tilde in pixel space once more. So that's the basic overview. This is really just without going into details, this is just the general diffusion process. Now let's explain some of the technicalities of it. So we're going to condition using what is called, we're going to condition using attention. So how that works is we're going to take conditioning information. This could be text. It could be a semantic map. So you could pass in, for example, a semantic segmentation of a view from a car and ask it to generate an image based on that. You can pass in other images, presentations. So this is a pretty general method, and we will pass that input into some feature extractor, tau sub theta, that extracts features from that type of text or from that type of data. So it could be an RNN for text, a transformer for text, a CNN for images. And we're going to condition on that embedding via cross-attention inside this UNet where we see QKB. And we'll go more into the details here. So yeah, we take input Y from a various modality, text, images, etc., pass it through a domain-specific encoder, tau sub theta, to get an intermediate representation, tau sub theta of Y. Then meanwhile, we take the output of a certain layer of our UNet, phi sub I of ZT, which we will then flatten to flatten across spatial dimensions to obtain a vector phi sub I of ZT. And that the activations from our unit phi sub I of zt will be our queries, which will then incorporate information from tau sub theta of y. So k and v will come from tau sub theta of y, and our query q will come from our unit phi sub I of zt. And from there, we just perform normal attention. We pass each of these outputs through a linear layer, and perform attention and to update our intermediate vectors z sub t. Okay, so that's how we incorporate that conditioning information, and then we can change our diffusion model objective just slightly to account for that conditioning information by now training our denoising network epsilon sub theta to denoise based on that conditional information. And that's given in the equation at the bottom. Okay, so the other thing I'd like to talk about more in detail is this DDIM sampling. So the key insight of, as I mentioned, of this paper is that we can skip steps in the reverse diffusion process. And the authors prove that this equation that you see here is sufficient to it is an equally valid equation for obtaining x sub I from x sub t. So what we're going to do is we're going to choose tau as a subset. Tau will be a sequence of t's, and it will be a subset of 0 to capital T. And the difference between each of the numbers in the sequence tau will be, we will call delta t. And then we can get x sub delta t by applying this formula, x sub delta t divided by basically applying different alpha sub t scaling terms to the output of a network that takes as input x sub t. So this will basically, to get our update for t, we will take a weighted combination of our original sample x sub t and our denoised sample epsilon sub theta of x sub t. And you can see some of the results. These images correspond to a diffusion model trained with capital T equals 1000, but instead of taking 1000 reverse diffusion steps, we are just going to take 10 or 100. And you can see that even between 10 and 100, there is almost no loss of fidelity in this reverse diffusion process. So this is a really powerful insight that we definitely want to take advantage of. Basically, anytime you use a diffusion model, you can sample from it more efficiently by using this DDIM sampling. So this is pretty much everything that you'll need for your lab next week. We're just going to talk about a couple of other variations on diffusion, just for your information for reference if you want to explore this more deeply. So we mentioned at the beginning these score-based generative models. So there's diffusion models, the terminology can be kind of confusing because they descend from two somewhat separate lines of research, one based on diffusion and the other based on score-based generative modeling. So score-based generative modeling says, basically, what if we can learn the gradient of p of x? instead of P of X itself. And it turns out that there are several reasons why learning the gradient might be easier than learning the probability density function itself. And which we won't go into here, but yeah, the gradient of P of X is also known as the score function. And so sampling from a diffusion model can, in another line of reasoning, can be interpreted as gradient ascent on the probability density function P of X to find a local maximum X hat. And so for that reason, the diffusion objective is sometimes called score matching, and diffusion models are sometimes called score-based generative models. So that's just kind of a note on terminology. If you see these score-based generative models, know that they're basically the same thing. One other thing, so I wanted to make mention of these continuous time diffusion models, because you'll probably see these come up more and more in the future. So this is a paper that shows that this discrete time Markov chain can be generalized to a continuous time stochastic differential equation given by this forward SDE at the top left of this figure. dx equals f of x t dt plus g of t dw. So we will call f of x t our probability flow ODE, and g of t dw will be our noise term. And so basically you can see in this diagram, there is a direct path shown in white between a sample from one distribution, x0, and the standard normal distribution, xt. But then by starting from any given point in x0, the stochastic differential version of that that probability flow ODE can allow you to generate a sample from x of t. So yeah, this kind of opens up a lot more possibilities of sampling algorithms by linking the theory of diffusion models to stochastic differential equations. And so we can use SDE solvers for sampling from our diffusion models. As well, having this kind of partition of information between a probability flow ODE and a noise term allows us to perform exact inference. As opposed to just density estimation, we can perform exact inference on samples from our data. So we can come up with exact log probabilities. And that is it for diffusion models. We will go over this more in class, and it's a lot of math, and the terminology can take a while to get used to. But hopefully this gives you a nice preview, and we will talk more about this on Monday.